Alrighty, so yesterday we finished the proof of the optimality of Huffman's code, and we started looking at the class of arithmetic codes. In particular, we saw Elias's. I'm not sure whether it's Elias or Elias. I'm not sure how he said his name, but anyway, this code, where what we do is we take our inputs, the x's, and if you remember, we compute this real value, which is the sum over all previous code words, just in the order that they come to us. You assume that an order is given. These are not sorted. We calculated the sum of the probabilities over the previous code words plus a half of the probability of the current code word. And we call this quantity Ri, some real number. We then take this real number and we calculate the ceiling of minus log pi plus 1. And we transmit that many binary digits of Ri as the code for xi. So that's Elias's code, and we can sort of visualize what's going on here. If I've got 3 different outcomes, and I've indicated the probability by the intervals associated with each drawn in black, then I'd get 3 numbers, R1, R2, and R3, which are the midpoints of those intervals. And what do? I transmit enough digits so that I know, okay, where this code word is. So I might have to focus in, okay. I transmit enough digits to know that I'm here. So if this was, for example, 1 over 4, then my code word associated with R1 is going to be 0, 0. Okay, so if this point, let's put some numbers in here, 0.42, 0.61. Let's assume that we have these probabilities. Why not? I'm just making some numbers up. So if I have something where x1 occurs with probability 0.42, x2 occurs with probability 0.219, and the rest is probability of x3, I'm going to transmit 0, 0, which tells me I'm in the first quarter of the space. If you know that whatever I send to you begins 0, 0, you know that I'm giving you a code word which lies in that first quarter of the space. There's only one code word there, R1, so you can identify which code word I've sent. I've sent X1. What about here? Well, in the top, I might have, again, R3 lies here, so I'm able to send a 1, 0, which identifies that I'm in the top segment of the space. Okay, actually, sorry, 1, 1. 1, 1. Okay, what about here? Well, here, because this is a small interval, the construction of Elias's code tells me I need to send a few more digits. So I'm probably going to send something like 0, 1, 1, because I'm sending more digits to account for the fact that this interval is fairly narrow. I don't know if it's exactly 0, 1, 1. I'm doing this in my head. But you get the idea. Because this interval is narrow, I'm going to have to send more digits so I can refine that probability down so that I know that everything in this interval begins 0, 1, 1, and that contains my R2. Does that make sense? Okay. So now that I have this gives me a code which it's not especially efficient. We can see that it's going to burn 1 extra digit compared to the optimum. So we can tell that when we have Elias's code, the expected code word length, okay, just from looking at this, is going to be less than h of x plus 2, which is not where we want to be. And in fact, we can do, on the other side, h of x plus 1. Because I've burnt that extra digit, but the advantage is I don't have to order the probabilities. And that gives me a huge advantage in practice because I don't have to take potentially a very large number of probabilities and sort them and store how I've sorted them. Okay, now that's Elias's code. The reason this is interesting is it feeds into arithmetic codes. Now, arithmetic codes, as I said yesterday, can be seen in a couple of different ways. One is just as the block version of Elias's code. You take Elias's code and you apply it to blocks of length n, then you're going to get something which is far more refined, and it generates what we call the arithmetic code. But there's a more fun way to see this. When I send a sequence, so what I'm going to do, if I send a sequence, I'm identifying a point in space. In fact, you can think I'm identifying an interval in space. So when I send, so what do I do? Let's try and draw a picture a little bit like this. So here's my space, here's my separation, and suppose I send the symbols 0, 0, 1, 1. Okay, so where is 0, 0, 1, 1? Okay, so first digits are 0, so I'm in the bottom half. I'm in the bottom quarter. I'm in the second eighth. I'm in the 4th 16th of space. So if I cut this up into 16 pieces, I would be somewhere like here. Okay, in fact, I would know that I have an interval that looks like this. And that's what I've told you. I've told you that I'm sending you a code word which begins 0011. Whatever it is. So I'm sending a real number beginning that way. So what I can do now, because I've identified this, you can actually go down and try and figure out what's going on. The first piece is clearly going to be an x1. What about next? Well, I do the same construction that I had before. I get this, so I'm going to have the first level, I get x1. Next level, well, my interval's still in this upper area here, so I'm going to send x3 is the next symbol. What about then? Well, I take this interval, I split it up, and I say, oh, I can't tell which code word I've sent now. There's multiple things in my interval, therefore I have to stop, and this is what I've told you. So 0011 corresponds, unsurprisingly, to x1, x3, given this construction. So by doing this repeatedly, we get something that's quite powerful. You'll notice the way that I did this decoding of this message, I just began, and I didn't have to go through the entire message. I could just start reading off digits, okay, because I knew where everything was. So by doing this, you have a block code which is completely recursive. So what do? I could write this out, but ultimately the picture tells the story as well as I'm going to be able to write anything down. So by sending a sequence, let's call it Q, we know we have a code word or a symbol, code symbol R in Q to Q plus 2 to the minus length of Q. So this is how many terms are in there. So we know that we're in this interval. In fact, we know that we're in, we can sort of leave it open on the left because I'm going to send the first digits. So I know I have something in here.
Sorry, what's in that power?
Sorry?
What's in the power?
It's the length of Q. Okay? I think that's right. Yeah, that's right. So by sending a sequence Q, where here I've thought of Q either as a sequence or as a binary expansion of a real number. So by doing this, I then just am saying that I need to identify which real number could possibly lie in there. And I do this completely recursively as I've described. So we use block coding to construct the R for each input sequence. Okay, so once I give you an input sequence, you figure out the interval, then you subdivide that interval and repeat. Now, this is why I'm not going to show you how to implement it, because it's a bit fiddly. The problem is you're not actually allowed to use real numbers. So when you implement this in a computer, you can't do it using floating point arithmetic because you will lose precision. So normal floating point arithmetic, you've got at most order 64 bits in a floating point number. So you don't have enough precision to represent what's going on accurately. So you have to write all of this while I explain it using real numbers. You actually do it all using binary sequences and having to manipulate them. So that's a bit painful. One beautiful thing is that it's completely online, and you can have this, you can implement it in a way that's completely online. What I mean is, if I now gave you, instead of this, I gave you an input which was 0011011011, and I said, I'm only interested in the first 2 digits, the first 2 symbols in the output. To do that, you could just go through and you go, oh, that gives me the first digit, conditional, that gives me the second digit, and I'm done. So I can do this completely pass through forwards, and I don't need to construct the whole code book. So the fact I'm not constructing the whole code book, I don't need to know what would encode as something else. I don't need to list all of those options. If I do a block code using something like a Huffman code, I need to enumerate all of the possible sequences. That becomes very, very inefficient because I've got to store this huge list of possible things I could encode. I've got to store that list. I've got to store how I'm coding them up, and transmitting that is expensive. So storing that information is expensive. So here we can do it directly. People happy with this construction? Okay. We can say one useful or nice thing about it. Let's try and understand the optimality we can get out of an arithmetic code. So, theorem. Let x1 through to xn be IID, random variables, from an input alphabet x with PMF P as usual. The arithmetic code based on length n blocks has average code word length bounded above by h of x1 through to xn plus 2, and hence per character average length hx plus 2 over n. So the point is, if I'm going to be encoding things in long blocks, and encoding in long blocks is not so evil because of this recursive nature of the construction of everything, then actually I don't care too much about this. I get something quite efficient. So how do we prove it? Well, ultimately it's the same as other block codes. So here we have an IID sequence, a source block, let's say x1, x2 up to xn occurs with probability product from I less than or equal to n of p xi. So that's just independence, which is the length of the interval it is associated with. Okay, every time I multiply, when I multiply out to get the length of this shorter interval, it's just the probability of the first block times the probability of the second block gives me the length here. Okay, we encode this using a block of length minus log probability of pi I less than or equal to n, plus 1, which is less than or equal to minus the log of the product I less than or equal to n p xi plus 2 xi. Just the usual bound, because I've got a ceiling, I bound it above by adding another 1. The average length is then bounded by minus the sum, well, I need the probability, I less than or equal to n pxi. So this is the probability of the sequence happening times the log, well, this upper bound on the length, I less than or equal to n pxi plus 2. And because probability is sum to 1, it doesn't matter whether I put that inside or outside the sum, which is, of course, equal to the entropy of x1 through to xn plus 2, which by independence is n h of x plus 2. And we divide by n to get the per character length. Happy? Now, key advantages of arithmetic codes. At the moment, we've been thinking about what we do when we're trying to encode something that's IID. But we don't actually need that. Suppose that we had something which followed a Markov chain. So every character, the distribution of the next character depends on the previous character. So once I'm in this block, I know the distribution for the next character is different. That's perfectly fine. I just change the way I split up the next interval. Okay, so at every level I can do this, and I just change how I split the next interval depending on those previous probabilities. Fine, you just implement it. It's no more difficult than doing a constant, doing the same split every time. So that's a relatively easy extension, which adds quite a lot of advantages. It'll generally give you something quite a bit smaller in terms of the bound. That just adds flexibility, so makes our lives fairly easy. The real problem is this floating point arithmetic. We just have to implement it far more carefully because we're not allowed to actually use real numbers. All right. So the last type of code I want to talk about is what's called variable to fixed codes. So far we've been looking at fixed to variable codes, where I give you a fixed input or a fixed length of a block, and then you return to me a string in the output alphabet, which is arbitrarily long. Now this is nice. We've worked with this in various ways, but it always has this problem. It can easily lose phase. So when I take my output string, I can read through this. If I have an error early on, it's going to destroy the estimates of everything. The decoded string is going to be completely different for everything that comes after that first error, okay? Because I can be knocked out of phase. So the other type of code that we'll consider are what are called variable to fixed codes. We're not going to do many of these, but we'll do one called Tunstall's code. So what do? We consider an input alphabet. Let's keep it simple. X is 1 through to m. Okay, and output, let's say y. We'll just focus on binary codes, 0, 1. We aim to find a set of input strings, W, So these are input strings of some length, which we encode in y to the d. So I have a fixed string length in the output. Okay. So how's this going to work? What do we need to know? Clearly, we need, okay, so how many strings can we encode in here? Well, the most we could encode is 2 to the d. So we need the size of w, which I'll just call k, to be less than or equal to 2 to the d. Because if I have more than 2 to the d input words, there's no way I can encode them all. Okay. We want our code to be proper. So we say it's proper. No element of w is a prefix of another element of w, and complete or exhaustive, i.e. every string in X star has a prefix in W. So why do I want this? I want it to be proper. This is the equivalent of a prefix property. So there's only one way to encode something. Okay? So once I've got a word, I know that it's not a prefix of another word. There's no other way I could encode that initial input code word. I want it to be complete so that no matter what string I give you in X star, there's some way to encode it. Well, in order for that to be the case, I just need to be able to encode the first bit of my string. So I need it to have a prefix which is a code word. So boring cases is where W is just the collection of single characters. So if W was just 1 to M, then that could work. Okay, it wouldn't be very efficient. It would just say I have my code words are 1 through to M, and I encode them using some digits in y to the d. So that would be a very simple example. Okay, so what we need is to find a set of code words which is proper and complete, where the number of code words is less than or equal 2 to the d. Because if I can do that, then I can construct a code. So this leads us to Tunstall's code. 1967. So this was Tunstall's PhD thesis. Again, the construction, the easiest way to do it is to do an example. So we start similarly, in some sense, to Fano's code. So we find the highest probability code word. So we start with code words 1 through to M. Okay, so we start with this basic set where we say we can just encode each character by itself. Find the highest probability code word. Okay, split it into M new code words by appending each of 1 through to m. Repeat until we can't fit in any more words. So really boring construction. Let's do an example. Okay, so let's say d equals 3, x, I'll say it's a and b just to make life a little bit more interesting. Just use a and b instead of numbers to prevent confusion. P, which is x, equals a, equals 0.7, and we will assume everything is IID. So what are we going to do? So our first step, I start with the code words a and b, and these have probabilities 0.7 and 0.3. So what am I going to do? I find the most likely code word, here it is, and I split it into, in our case, two options, A and B. So this is AA and AB. What are the probabilities at this point? It's 0.49, 0.3 still, and 0.21. I now find the highest probability code word. Here it is. I split this into two, so I get AAA and AAB with probabilities 0.343, 0.147. I then find the highest probability code word. I split it into two pieces. So I get AAAB, AAAB with probabilities 0.2401 and 0.1029. How many code words have I used so far? Well, I know that I've got 2 to the 3, so 8 code words I'm allowed to use. So far I have 1, 2, 3, 4, 5 code words that I've used. So I can keep going. Biggest probability is now here, so let's split this into two. 0.3, so I get BA and BB. And where are we? So this has probability 0.21 and 0.21. No, 0.09. Okay, next. Oh, split this one again. So A, B, A. So 5 A's here. With probabilities. So 5 A's has probability 0.16807 and 3 A's, a B and an A. Have I done this right? I think I did this right. 4 A's and a B. Yes. A, B. That's better. 4 A's and a B is 0.07203. 1, 2, 3, 4, 5, 6, 7. I can do one more split, and I will choose to split this one. I have a choice. It's not unique, so I can deal with it arbitrarily using Tunstall's algorithm. Here's an example. So let's split this into BAB and BAA and BAB, which have probabilities. BAA is 0.147 and BAB is 0.063. And I'm done. I've run out of code words. So now I identify my code words at the end. Here they are. So this is everything which is a leaf becomes a code word. And I have 8 code words, and I filled up my space. There we are. All right, so this is Tunstall's construction. And so now all I have to do, I can just allocate these arbitrarily. I just put them in some order. So I might have A, 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 B, A, 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 B, A, A, B, B, A, A, B, A, B, B, B. 1, 2, 3, 4, 5, 6, 7. Which one have I forgotten? BB. AB. I forgot to circle it. There we go, AB. And so now I've got my 8 code words, so I just assign them arbitrarily a 3-digit binary string. So 000, 001, 010, 011, 100, 101, 110, 111. So now I take whatever string I have, and I can just use this by reading off. So if I gave you the string A, B, A, B, A, you look at this and you go, right, where's the first code word? There's a code word, AAB. So I send this as 011. Next I've got AB, code word, 111. AA, oh, it's not a code word. I may have to pad on the right-hand side. So let's suppose I padded with A's, because I have to get something long enough, just like when I'm using a block code, you have to pad on the right-hand side. So if I pad with a sequence of A's, that's enough to make sure I have a code word, 000. And that's what I would transmit. And the point here is that I've now got something which separates cleanly into blocks of length 3. I've got fixed output lengths, but variable input lengths. Everyone happy with that construction? So on problem sheet 3, I've given you the job of implementing this. Okay? You can do it based on the Huffman code which I've put online, particularly the encoder and the decoder, but because it's variable to fixed, not fixed to variable, you're going to have to rearrange things and think about how to manipulate the strings. Yes?
So this was according to the definition of completeness, it's not complete, right? Because we take the string A, there is no...
Yes, so this then would be complete up to padding. Okay, so if I say I'm always allowed to follow whatever I get by an infinite string of A's, then this is complete. Okay, you're perfectly correct. One thing to notice, again, if I asked you to do this code but not assuming IID, then that would be perfectly easy. You say, if the first character is an A, I can change these probabilities. I don't need these probabilities to just be multiplied by the unconditional probabilities. I can say, after an A, maybe it's more likely to have a B than an A. So maybe these two numbers would flip over in this case. That's perfectly fine. You just go through and you do it using the conditional probabilities at each step. So you can have that path dependence in the Tunstall code, no problem, doesn't change the construction. So this is easy to do. Is it optimal? Well, we have to be a bit careful in what we mean by optimal, but there is a sense in which it is optimal. So theorem. And this is just a beautiful proof. It really is. So suppose we have an IID sequence x1, x2, of inputs in X. And we'll see that assumption is not so critical if we change the construction accordingly. Among variable to fixed codes which are proper and complete, with the correction that you just pointed out, that we can always pad on the right if we need to. Tunstall's code is optimal in the sense that it maximizes the expected length of the input string, which is encoded as a single sequence in YD. So we can't talk about optimality the same way. Previously we talked about we wanted to minimize the expected length of the output. Here the output length is fixed, so I want to maximize the expected length of the input instead. And in this sense we can give an optimality result. Okay, proof. So I'm going to basically sketch it out a little bit, but you'll see how it all fits together. Okay, suppose, for simplicity, we allow m output messages. M is equal to 2 to the d. Okay, it just saves me writing 2 to the d everywhere. Okay. Any proper and complete code corresponds to an M-ary tree. So this is completely analogous to what we saw for when we were dealing with Huffman codes. We said, oh, those are binary trees. Here we have an M-ary tree because at every step there are M different options. Sorry, is it M? No. Oh, I don't want M. Sorry. No, ignore this. So, number. We'll just allow an integer number of messages. It actually doesn't matter. Sorry, I said something completely stupid. Ignore everything I just said. So we're going to have an integer number of output messages. So 2 to the d. Any proper and complete code corresponds to an M-ary tree because you have to always be able to decide what's the next character I'm going to try and encode. So because it is proper, it's a tree, and because it's complete, it must be M-ary. Because you always have to be able, if you're going to append something, you have to be able to append all M options for what the next character could be. Okay, so when you think about I've got a string so far, if I've got more terms in the code word, I've got to be able to fit in precisely M of them at every step. So I'm going to get here. Here I had a binary tree because I had M equals 2 inputs in X. Okay. So now we know an M-ary tree has k times m minus 1 plus m leaves. Why? Well, every time I split a node, I add m minus 1 new terms. So m minus 1 new leaves. So every time I do a split, when I build up a tree, I'm always adding m minus 1, and I do this an integer number of times, okay, where k, what's k, you can actually say what it is the number of internal non-root, non-leaf nodes in the tree. Okay, so here you can see which are my internal nodes in my example. Well, it's not the root, but I've got 1, 2, 3, 4 internal nodes in this tree. So for this example, k would be 4, and that gives me the correct number of leaves. Okay, so let kt denote the set of internal nodes in T. So if I give you a tree, what can we say? All right, well, how many times, when I do this splitting, how many times can I do it? Well, every time we split, we can go back just a moment, we can notice that when we repeat, we keep repeating. So after k steps, we have k m minus 1 plus m leaves. So we can do exactly k equals the floor of 2 to the d minus m over m minus 1 iterations. Just going back, every time I split, I'm adding more nodes. I'm adding m minus 1 nodes. At the most, I've got 2 to the d leaves at the end of the day. So this is how many times I'm allowed to split. Okay, given that, what can we say? Well, we want to compute the average length of the input message. We can compute the average length of the input message as 1 plus the sum of Pn, where Pn is the probability associated with node n, rather. So what's going on here? I want to compute the average length of what I can input. Okay, if my tree only has the first thing, it has no internal nodes, the average length is 1. Boring. So now, suppose that I do just this first split here. What's the average length? Well, I've got 1, the first step, and then I'm going to add 1. What's the chance I add another one? Well, it's this probability here, which I'd call P of this node. Okay, so that's the chance that I get to this point and have to add another one. Okay, when I've done this full tree, then I can compute the average length by going, well, it's 1 plus this probability that I get to here. Then I'm going to add 1 for this step. This probability I get to here, add 1 for this step. This probability I get to here, add 1 for this step. And do this over everything that's an internal node. So I can compute this sum here. And that is the expected length of an input, which is a rather sneaky way of writing it down. Why is it sneaky? Hence, if we wish to find an optimal code, we need to maximize the sum KTPN over emery trees T with the desired size. So I've got the desired number of leaves, I should say. Well, the number of leaves, I could really say every time I add I add an internal node, I'm adding the same number of leaves, so the desired number of internal nodes. Okay, fine. So now, let's forget that I have to have a tree. Let's just forget this completely. Let's consider the infinite family of Emery trees. Etc. If I just, each of these would have a probability associated with it. I can compute for a string by going through A, B, C. I'd get a probability here. I'd get a probability on every internal node. I'm just trying to find, I want to maximize this probability. So the greedy maximization would be just to select the nodes that have the highest probability. Okay, don't think about the fact they have to form a tree. Don't think about anything else. How do you maximize a sum? You pick the biggest elements. So as k equals 2 to the d minus m over m minus 1 equals the size of kt is fixed, just pick the k terms with highest probability. Okay, the problem is they may or may not form a tree. But if they did form a tree, then we would have solved our problem, because we're just picking the terms with the biggest probability. Okay, so where's the probability going to be biggest? Well, clearly this has probability 1, so that's going to be the biggest. And then you notice that all of these are smaller than 1 because they correspond to paths where I've added an extra conditional statement. So probability always goes down. So the next most likely ones are going to be something here. Suppose it's this one. And what am I doing when I try and find the maximum elements? I'm precisely following Tunstall's algorithm. If I pick out the biggest one, then I pick out the next biggest one, then I pick out the next biggest one. That precisely follows Tunstall's algorithm because probability always decreases. So as probabilities En are decreasing as we move away from the root, this is Tunstall's algorithm. It just selects the k terms with the highest probabilities. So it's selecting k terms with the highest probabilities in the tree. Therefore, it has maximized this over all possible trees. It's maximized this over all possible selections of nodes from the infinite tree. And therefore, it must be optimal in the desired sense. So we've maximized this expected probability. And that's how we know Tunstall's code is optimal. Yes?
Just to check, when you wrote in blue, consider the infinite family of our trees, do you mean just the infinite Emery tree?
So yeah, I consider the infinite Emery tree.
Just wrote the infinite family of Emery.
Yeah, okay, the infinite Emery tree. And then I'm picking subtrees from the infinite Emery tree. That's maybe a better way to express it. Okay, so by picking this many subnodes, I picked out, hopefully, a subtree. Turns out that I do pick a subtree. And so we're golden. We know that we've got an optimal code in this sense. Okay, there are various other results that we could show. So we can show, for example, we could show that d over the expected length of input, that this, must be greater than or equal to h of x. So we still get the Shannon bound in a different form, where we now have the expected length of the input and just a single output here. We can vary this to allow Markov chain inputs. And one of the beautiful things about doing this, one, it's easy to do, and two, because we've got that block structure, you know that all of the relationships are going to be easily preserved. Okay, everything follows very easily. You know that this value, this block, depends on this block in a fairly clean way, not on the infinite sequence of what's come before. So if you have Markov chain inputs, then you're going to get Markov chain outputs with a block structure. So you just take each block, and that at a block level forms a Markov chain. There are lots of other things we could do. So there are what are called block arithmetic codes. These are a variation on arithmetic coding using blocks. It gives you a variable to fixed code similar to Tunstall, slightly less optimal, but can be done in an online fashion like the arithmetic coding. So you can run this completely online. There's also then, from here you get to what are called the Lempel-Ziv codes. Basically, the problem with every code we've seen so far is you have to know the probabilities before you start. The fact that we can encode a Markov chain means I can change the probabilities as I go. So what Lempel-Ziv does is it dynamically estimates those probabilities based on what you've seen already. So you start by saying, I don't know what's going on, and as you move through, you update the probabilities based on the characters you've already seen, so that you can become closer and closer to optimal without knowing the distribution before you start. So this is Lempel-Ziv and Lempel-Ziv-Welsh are what are usually used in zip files because they are better and easier to encode, and you don't need that full knowledge of the distribution. Okay, that's all we're going to do on these compression type codes. So next week we're going to start the second half of the course, which looks at what do we do when we're trying to transmit information. We might have encoded it, but we're going to transmit it over a noisy channel. So what we send is not what we hear, and how do we do that in an efficient way?